Hi everyone, welcome to the first lecture of Solitons. So today I'll give a general introduction to the subject, and so I will exceptionally use slides since I want to show you some videos and animations. But later on, all the other lectures will be delivered on a visualizer, and I'll write in real time. The history of the subject starts in 1834, when a young Scottish engineer called John Scott Russell, here portrayed at a later time, was at the Union Canal near Edinburgh. John Scott Russell was working to improve the design of canal boats. So he was observing a boat pulled by a pair of horses when he made the following interesting observation. So let's hear from his own words.
I was observing the motion of a boat which was rapidly drawn along a narrow channel by a pair of horses, when the boat suddenly stopped. Not so the mass of water in the channel which it had put in motion. It accumulated round the prow of the vessel in a state of violent agitation, then suddenly leaving it behind, rolled forward with great velocity, assuming the form of a large solitary elevation, around it, smooth and well-defined heap of water, which continued its course along the channel, apparently without change of form or diminution of speed. I followed it on horseback, and overtook it still rolling on at a rate of some 8 or 9 miles an hour, preserving its original figure some 30 feet long and a foot to a foot and a half in height. Its height gradually diminished, and after a chase of 1 or 2 miles I lost it in the windings of the channel. Such, in the month of August 1834, was my first chance interview with that singular and beautiful phenomenon which I have called the wave of translation.
John Scott Russell was convinced that his observation was very important, and so he carried out a few experiments to measure the physical properties of this wave of translation. So here we can see depicted two kinds of experiments, one in which the wave is created by pushing a wall towards the interior of an artificial channel, or alternatively, you could also drop a weight to create the wave. And so Scott Russell measured a number of quantities such as the speed of the wave, the height of the wave, the width of the wave, and discovered some empirical relations among them. Unfortunately, the rest of the scientific community didn't pay a lot of attention to what John Scott Russell reported. And it took several decades for the mathematics necessary to describe Scott Russell's observation to be developed, and about a century, or actually even more than a century, for the rest of the scientific community to actually start appreciating the very peculiar properties of this wave of translation. The solitary wave translations can be studied in the lab, essentially following the same experiments that John Scott Russell himself carried out in the 19th century. And so let's watch a video here of a wave of translation. So we can see that some weight of water is dropped, and this creates a wave, a single solitary wave, which, as you can see, travels keeping a fixed shape and with constant velocity. There it bounces off a wall and comes back. Another wave is created, and now there are two solitary waves going in opposite directions. So let's watch what happens next. So you see that, strangely enough, the two waves seem to go across one another without much effect on them. So we'll return to that in a few minutes. But these solitary waves of translations are not just an academic curiosity or objects that can be created in a lab. In fact, they appear in nature under a number of circumstances. So here is an example. This video was shot on the spring equinox last year. So the equinox is when the tide coming from the sea, in this case the Atlantic Ocean, is at the highest, and when it enters the estuary of the Severn, which has a shape of a funnel, it creates this the water rises and it creates this solitary elevation, this solitary wave, which goes on for several miles, up to 10 or 20 miles inside the estuary of the Severn and into the Bristol Channel. John Scott Russell's solitary wave of translation nowadays is called the soliton, following terms coined by Zabuzki and Kruskal in the paper which restarted the subject in 1965. So we will use the following definition of a soliton, which reproduces the key observation that John Scott Russell made and that we could see from the previous videos. So we'll call a soliton a special solution of a special type of nonlinear partial differential equation that we'll normally call wave equation, which has 3 properties. So the first property is that a soliton has to be localized. So sometimes we'll say that it's a lump of energy or a lump of field. So property 1, that the soliton is localized, is the reason for the suffix on in the word soliton, because soliton is a special type of solution of a wave equation which behaves very much like a particle in that it's localized in space. And since the suffix on is normally reserved for particles like the electron, the photon, or the Higgs boson, Zabuzki and Kruskal coined the word soliton. So that's property 1. The soliton has to be a localized solution of the wave equation. Property 2 that defines soliton is that it moves with the constant shape and velocity in isolation, meaning when it's far away from other solitons or other waves. And this is what we've seen precisely in the video of a soliton created in a lab, and it's also what John Scott Russell observed in 1834. So finally, there is a third property, which, as we'll appreciate later, is really the key property that defines a soliton. And this is property 3, that a soliton is preserved under collisions with other solitons. Namely, if 2 solitons collide, they have to reemerge with the same shapes and velocities. So similar to what we saw in the video of the 2 solitary waves, which collided head-on, but somehow the 2 waves seem to keep going afterwards, more or less keeping the same shapes and the same velocities that they had before the collision. It took about half a century after John Scott Russell's observation for a mathematical equation to appear, which can describe the empirical observation made by John Scott Russell. So this is known as the Korteweg-de Vries or KdV equation that we see here. We'll look at the various terms in a second. And it was written down by 2 Dutch mathematicians called Korteweg and de Vries in 1895. But in fact, the same equation was discovered about a couple of decades earlier by a French scientist called Boussinesq. So it should actually be called the Boussinesq equation. But it's often the case in science that things are named after the last persons who discovered them, not after the first one. So we'll call this equation the KdV or Korteweg-de Vries equation in this course. So let's first discuss the various ingredients. So first of all, we have U, which is what we call the field, and that's a function of 2 variables, x and t, and U represents the height of a wave of water at position x and time t. So here we're discussing waves moving in 1 dimension, essentially following the observation of just Scott Russell of a wave in the canal, where what happens along the width of the canal doesn't really matter. So the coordinate x parameterizes the position of the water, say, along the canal, and t is time. So then there are 3 terms in the KdV equation, and we see there are subscripts. Subscripts denote partial derivatives. So the first term, ut, is a partial derivative of u, the height of the wave, with respect to time. ux, which appears in the second term multiplied by u, is the partial derivative of u with respect to x. And uxxx is the third partial derivative of u with respect to x. So it turns out that the KdV equation describes the long wavelength and shallow water limit of the physical wave equation in one space dimension if one chooses a suitable reference frame which moves along with the wave. So if you're interested in the details of the derivation of this equation from the more complicated equation that describes the physics of water waves moving in one space dimension, I recommend section 1.2 of the book by Drazen and Johnson, which has more details, but we won't need those details for this course, so we'll just focus on the KdV equation itself. Let's stare at the KdV equation a bit more. So the first thing to notice is that the second term here contains u, the field, which measures the height of the water, times its first partial derivative ux. So in particular, we see that the KdV equation, because of this second term, is nonlinear. So that means that the superposition principle fails. So I remind you that the superposition principle holds for linear equations, and it tells us that if we rescale a solution by a constant, we get another solution, or if we add two solutions, we get the third solution. Unfortunately, here the superposition principle doesn't apply, so we cannot immediately add up different solutions. So this might sound disappointing at first, but actually it's a key to the very peculiar properties of these equations. So the second thing to notice is that the equation looks rather simple, so it can be written in half a line, but it turns out that it hides a very rich mathematical structure, which we will explore and investigate in the course of the year. A final point to notice is that the KdV equation is of first order in time, so the time derivative only appears here in the first term. And this tells us that given an initial condition that specifies the profile of the field u as a function of x at time 0, we can use the KdV equation, we can integrate the KdV equation to find the solution u as a function of x at later times t. So in particular, given the initial condition u of x at time 0, we can use the KdV equation, which determines the first derivative of u with respect to time, to find the profile of the field u as a function of x at an infinitesimal time later, dt. And if we iterate this infinitesimal procedure, or rather we integrate the equation, we can find the full solution u of x and t. So what we'll do next is to study the time evolution of a few given initial conditions with the help of a computer. So we'll start by looking at the initial condition where u of x at time 0 is 2 over hyperbolic cosine squared of x, which has this very nice localized form. But before we evolve the field in time using the full KdV equation, let's study what happens if we drop one of the three terms. So we cannot really drop the time derivative term, or we will completely lose time evolution. So let's study in turn what happens if we drop the second term, the nonlinear term, or if we drop the third term, which involves the three spatial derivatives. So let's see what happens if we drop the middle term, which was responsible for nonlinearity. So what we'll get is a so-called linearized KdV equation. What we see is that the initial localized wave disperses. In particular, it spreads out. So there are these waves which move towards x equal minus infinity. And if you fix the value of x, the amplitude of the wave goes to 0 as time goes to infinity. So we'll come back to this, the precise meaning of dispersion, in the next lecture. So the next option is to keep the nonlinear term, but drop the third term, which was responsible for dispersions, and we'll get the so-called dispersionless KdV equation. So here's what happens, that the wave remains localized, but it piles up towards the right, and after a finite time, it breaks down. So please ignore this bit here. This is an artifact of the numerics. But what happens is essentially that the wave piles up to the right until the profile becomes vertical. At some point, the first derivative goes to infinity and the wave breaks down. And as you can see here, this happens after a finite time, which we call the breaking time. And both the solution and this finite time can be computed using the so-called method of characteristics that some of you may study in the PD module. So we will not enter into the details of the methods of characteristics, but there is a note on Duo that you can read if you're interested to see how the solution is computed and how the breaking time is also calculated. Right, so what we observed is that if we drop the middle term, then the wave, the initial localized wave, is destroyed because it disperses towards the left. On the other hand, if we drop the third term, the initial localized wave also doesn't move at constant velocity and keeps its shape, but rather it piles up towards the right. If you're an optimist, you might hope that when we keep both the second and the third terms, the two phenomena that destroy the initial localized wave can somehow counterbalance one another. So let's see what happens if we keep all the terms in the KdV equation. So we indeed find a solitary traveling wave which keeps its shape and moves at constant velocity. So please ignore the bit here. This is because I impose periodic boundary conditions. So x equal 10 is identified with x equal minus 10 to make the numerics possible. And also this will become useful later on today. Nice, but you might complain that the initial condition that I chose was rather special. So to answer that question, let's consider a slightly more general initial condition where instead of a factor of 2 in the numerator, we'll have a factor of n times n plus 1 when n is a positive real number. So in particular, when n is 1, we get 1 times 2, which is 2. So we go back to the initial condition that we studied in the last few minutes. So what I'll do next is to show a few animations of what happens for different values of n. And again, for convenience, I've imposed periodic spatial boundary conditions. I will return to that later. So let's start with n equal 1/2 or 0.5. So what we see is that the initial localized wave disperses. And there are these waves moving to the left, which here re-enter because of the periodicity that I've imposed. So no solitons. Next, n equal 1. This is what we studied earlier. So we just find a single soliton that moves to the right at constant velocity, keeping its shape fixed. Next, n equal 1.5, and we see that the initial condition breaks down into a soliton which moves to the right plus some dispersive waves. Next, n equal 2. So we see that the initial condition breaks down into two solitons which both move to the right. So we'll focus on what happens when they collide later on. But for now, the important thing to notice is that of the two solitons, the narrower one is faster and also taller, and the larger one is lower and also shorter. So next we move on to n equal 2.5, and we see again two solitons moving to the right plus some dispersive waves moving to the left. Finally, let's move on to n equal 3, where we find that 3 separate solitons with different heights, widths, and speeds, all moving to the right. Let's summarize the results of these numerical experiments. When the parameter n is an integer, we observe that the initial localized wave splits into exactly n different solitons which move to the right. On the other hand, when n was not an integer, we found that the initial wave split into a number of solitons which is equal to the integer part of n. And these solitons all move to the right, but in addition, there are also some dispersing waves which move to the left. So if one stares at these animations closely, or if one plots the time evolution, it's not too hard to show that, in fact, the speed of a soliton is proportional to its height, and the width of a soliton is proportional to the height raised to the power -1/2. So these results confirm the empirical observations of John Scott Russell, and we will rederive them analytically in a few lectures. So while solitons by themselves move at constant velocity, keeping a fixed shape, the fun really begins when two different solitons meet, as we saw already in the video of the two water solitons created in a lab, and in this numerical time evolutions of KdV initial condition with the periodic boundary conditions. So as I said, and well, as we observed, the KdV soliton always moves to the right, and its speed is proportional to its height. So if we have a taller soliton which is following a shorter soliton, the taller soliton will catch up with the shorter one and will eventually overtake it. Let's watch again what happens. We'll watch it a few times. So there are a couple of interesting things to observe. So first of all, the two solitons indeed emerge from the collision with the same shapes and velocities. So in keeping with the third defining property of a soliton. And this is quite surprising because the KdV equation is nonlinear, so the superposition principle doesn't apply. And the other interesting thing to observe is that the height of the taller wave somehow decreased while it was overtaking the shorter wave. And this is very unusual. Note, by the way, that while the two solitons did emerge from the collision with the same shapes and velocity that they had before the collision, they did not emerge where they would have been in the absence of the other soliton. This might be a little hard to see from this animation. So instead, let's consider this contour plot of the energy density. So here, dark regions or blue regions are regions where there is very little energy density, and the light regions have a high energy density. So in particular, we see that this is the trajectory of the faster soliton, and this is the trajectory of the slower soliton. So here we are at early times before the collision, and the faster soliton gets closer to the slower soliton. Then there is this collision, and afterwards the faster soliton emerges ahead of the slower soliton. But the interesting thing to observe here is that the position of the slower soliton is behind where it would have been in the absence of the other soliton. So in the absence of the faster soliton, the slower soliton would have been somewhere around here, whereas it's behind by a little bit. And similarly, the faster soliton would have been here, but instead it is advanced by a little bit. And this advancement or retirement is called the phase shift. And it's precisely the phase shift that encodes all the properties of the interactions between the two solitons. So we will rederive the key properties of this plot later in the term. And in particular, we'll also be able to calculate the phase shift that two KdV solitons undergo when they collide. John Scott Russell himself actually noticed many of the unusual properties of these solitons, and as I said, he was convinced that his observations were very important, but it took more than a century for the mathematics and the rest of the scientific community to catch up with John Scott Russell's intuition. And the modern revival follows the work of Zabusky and Kruskal, who built on previous work of Fermi Pasta, Ulam, and Singu, which involved the very first numerical simulations using computers. The results of Fermi and collaborators occupy a very special role in the development of modern science, because in particular they provided a counterexample to the very general expectation that all physical systems would reach thermal equilibrium if you wait long enough. So I will not delve into the details of what they did, but if you are taking statistical mechanics, I recommend you to read the footnotes in the lecture notes about their numerical results. And what Zabusky and Kruskal did later on in 1965 was to understand that actually the KdV equation describes the physical system that Fermi, Pasta, Ulam, and Singu studied in a certain so-called continuum limit that we will study later. And they realized that the special properties of the KdV equation actually explain why this physical system doesn't thermalize over time, but actually displays periodic behavior. In the animation here, this is the time evolution of a sinusoidal initial condition with periodic boundary conditions. And that's precisely what Zabusky and Kruskal studied. So you can see that it broke down into a number or a train of different solitons. Those are the various degrees of freedom of the system, which move independently. So it looks like the system has thermalized in the sense that it has spread out its energy evenly among all its degrees of freedom. But if you wait long enough, then it turns out that the system goes back to the original configuration. So here is where I stopped my numerical simulation, because the numerics was getting a bit blurry already. But if you look carefully, you can see that this is exactly the train of solitons that we had at the beginning. And if your numerics is better and you wait a little longer, then you will see the sinusoidal wave appear again. Okay, to summarize, we said that the soliton is a special solution of a special nonlinear partial differential equation, which is localized, which moves with constant shape and velocity in isolation, and that is preserved under collisions with other solitons. So only very special field theories or wave equations admit solitons as defined above. These are called integrable field theories or integrable wave equations, and are usually defined in one space and one time dimensions. So in this course, we'll study mainly two examples, one of which is the KdV equation that we have already encountered. And the second one is the Sine-Gordon equation, which takes this form here, where u is an angular variable, which is periodic with periodicity 2 pi. So since the work of Zabudski and Kruskal, solitons have been studied in depth, and they found applications in a number of fields. So they are useful in applied mathematics, not just to describe water waves, but also in the study of optical fibers, electronics, and biological systems. They're also very important in high energy physics in the context of particle physics and gauge theory, as well as string theory. And finally, they have strong links to pure mathematics because in the study of solitons, several special functions arise, which also link to algebraic geometry and group theory. We won't have time really to study all these applications, but what you will learn in this course are a few interesting bits. So first, in this term, you'll learn how to find the exact soliton solutions of special wave equations. And you'll also learn what happens when different solitons collide. So what we'll do from now on is to study solitons analytically with pen and paper. So occasionally I will show animations of time evolution, but if you don't like numerics, rest assured that we'll derive all our results with pen and paper. So then you will learn what are the key properties that make this soliton so special. So we'll see a little bit of that in this term, but this will be the main focus of the next term, which will be taught by Patrick Dory. And also in the second term, what you will study is how in practice solitons are really the building blocks of general nonlinear waves. So that's for the next term, but this term instead we will study pure solitons without dispersion. And to develop some intuition, let's first look at a discrete model which exhibits solitons, this so-called cellular automaton. This is called the ball and box model, and it's a simpler version of the KdV equation with discrete space and time. So space will be labeled by integers, and time will also be labeled by integers. So we'll think of the integers in space as boxes, and the configuration of the system at a given time t is specified by saying which boxes are filled by balls. So in particular here we see that boxes 3, 4, 5, and 6 are filled by a ball. So that is the analog of having a bump in the wave, and the boxes which are empty represents flat water. Then we need to specify how the system evolves in time when t goes to t+1, and this is given by the ball and box rule, which goes as follows. So we are instructed to work from left to right and move the leftmost unmoved ball into the first empty box to its right. And then we need to repeat this procedure until all balls have been moved exactly once. So let's consider this example first. So if we want to evolve from t equals 0 to t equals 1, we start from the left, the ball in position 3, and we move it into the first empty box to its right, which is box 7. So here it goes at the time equal 1. So next we do the same for the ball at position 4 at time equals 0, and position box 5 and 6 are occupied by the other two balls, and box 7 we have also just occupied, so this will move to position 8. And similarly for the other two. So what we found here is that the 4 consecutive balls move to the right by 4 boxes in 1 unit of time. So we can say that a width 4 soliton moves with velocity equal to 4. So the velocity seems to be equal to the width. So now let's experiment with collisions, and in particular, I'm going to give you the following exercise. where we consider a length m soliton, which will move with velocity m, which follows a shorter soliton of length n, where m is larger than n. And you're asked to evolve the system in time until the faster soliton overtakes the slower one, and then to calculate the phase shifts of the two solitons. So now please pause the video, take a couple of your favorite values of m and n, and experiment with this exercise. Now, if you've done your exercise correctly, you should have found that the phase shift is equal to plus or minus 2n. So in particular, the faster soliton has a positive phase shift, which is twice the length of the slower or shorter soliton, and the phase shift of the slower soliton is the negative of that. In particular, this is an example. And in exercise 4, which you will look at in the first homework, you will have to derive this result in full generality. Finally, let me mention that the ball and box model can be generalized in a number of ways. So in particular, you can consider generalization in which there are balls of different colors. So let's consider in particular the case of two colors where you have blue and red balls. And then the ball and box rule with two colors is essentially the same as before, but you first move all the balls of one color, say the blue balls according to the standard ball and box rule. And once you're done with that, you do the same for the balls of the other color, the red balls. Here's an example. If you want to familiarize yourself with the rule, please check that I didn't make any mistakes, and if so, please let me know. In particular, there are a couple of questions that I'll ask you to investigate in the exercises. So the first question is, what are the solitons in this two-color ball and box model, and what are their speeds? And secondly, you might want to study what happens when these solitons collide. This, by the way, is a start exercise, which means that it's a little harder than normal exercises. All right, with this I'm done for today. Please play with these exercises and see you next time.